Our next speaker for the next session is Professor Ray Weiss. We'll be doing a live Skype with him.
Okay, good. So let me begin. First of all, I ask for your forgiveness that this had all to be done this way. It has partly to do with my ignorance about passports. And I didn't realize that my passport had to be 6 months before expiration, and I got stopped. So you have now this inconvenience of having to deal with all this gadgetry. So let me begin by saying that most of you know about the Einstein change in gravitation, the way to look at gravitation, that happened in 2015. It was a revolution, and the thing is that it predicted various things that were actually found. In fact, one of the predictions was that the period of the perihelion advance of Mercury, which is the motion of Mercury around the sun, which had not been understood prior to that time so well, was actually explained. And Einstein got an enormous encouragement out of that. In 2016, and now let me ask for the slide. In 2016, he came up with a perturbation theory of his more formal theory that he had formulated in 2015. And in that, he goes back and he does, in linearized theory, he shows that Newton is recovered from his theory. He shows that the perihelion can be calculated that way again. And the new thing in the theory is that he predicts gravitational waves. And he shows that they are waves that come from non-spherical, well, he doesn't know this, but he makes a mistake, but they do come from non-spherically symmetric accelerated masses. In fact, in that paper, in that 1916 paper, if one reads it carefully, you'll see that he actually gets gravitational waves from spherically symmetric expansion and contraction, which is completely wrong, and then he has to rewrite it all in 1918. But that's neither here nor there. He says something interesting. We'll get to that paper in 1916 in a second. But the important thing that comes out of that paper is that they propagated the speed of light, which we now know is true. And the second thing is that they are transverse waves that cause tension and compression in the space perpendicular to the direction in which they flow. So now if you hit the button, you will see this motion. That is the transverse motion generated by the dots. There you go. Just let it go. Good. This will make people a little dizzy if they look at it too long. But the way to think about it is this is a transverse wave coming out at you from the screen. And what you see is that red dot in the middle, or that square. And that's you. And those dots are sprinkled out in space, and they represent the motion that the waves impart to space and time. But in this case, it's all space. And you'll notice two things in that. There's a compression in one dimension, that's transverse to the wave, and a expansion in the other. And the other thing you'll notice is that when you look at the dots that are very far away from the red one in the middle, you'll notice that they are moving a lot more than the one that are very close to it. And that whole representation of that figure is one where the change in the distance between the motion of the dot divided by the separation of the dots is a constant. In other words, delta L divided by L, where L is the separation of the dots, is a constant everywhere in that picture. It's negative in one dimension and positive in the other. It's very much like stretching a rubber band. And that is the quantity that's then becomes the field quantity in a gravitational wave is the strain. That's delta L divided by L. So why don't we go to the next slide? And here is the beginning of the trouble that, in fact, made this the difficult area. This is a little quote that comes out of the 1916 paper. And I don't want to belabor it. It's in German, and I've underlined it there, but you can read it in English. And what it's talking about is that the equation that is on the top of the page. And that A is effectively the power in the gravitational wave. And then the stuff on the right is derivatives of the motion of the masses that are making the wave. And Einstein makes this very bold and actually quite dramatic statement that he says, in any case one can think of, A, that the amount of power in the wave will have a practically vanishing value. And that's an interesting statement. In fact, it's also true for the 2018 paper, which doesn't have the 1918 paper, which doesn't have this mistake in it. But the thing is, let's see why Einstein may have come up with this. I'll be presumptive and become Einstein. I've asked the Einstein historians to try to find the back of the envelope that has the derivation, or the notebook in which this derivation is, but we couldn't find it. Anyway, so look at the equation. H is the strain, and that's equal to, let's look at the second version of it, G, that's the Newtonian constant, times the mass of the system, divided by the distance you're away from it, divided by c squared. That first piece of it, Gm over rc squared, is a measure of the strength of gravity. And in fact, it's a useful number to know. It's a dimensionless constant, a dimensionless number. And for example, on the Earth that we're at, it's about 10 to the minus 10. On the surface of the sun, it's about 10 to the minus 6. At the point of at the surface of a neutron star, it might be 10 to the minus 1. And at the event horizon of a black hole, it's around 1. So you can see we live in a very weak field. Now, the second part of that expression, v squared over c squared, is just the non-spherical motion of the system. And for example, what I gave two examples here. One is a train colliding with two trains colliding. And that's a motion which is completely linear. And so he put some numbers into this, and I put the mass of 10 kilograms, the velocity of 100 kilometers per hour, a collision time of a third of a second, and you have to be out far enough so you're in the radiation zone. You're not in the induction zone. So 300 kilometers, and you get an H value which is truly infinitesimal. Nobody can measure that, and Einstein must have come up with that and been horrified. So he might have well looked at the thing that's on the right of the slide, where you have you look at a binary star system, which were certainly known in those days. The size of the galaxy was not known, but so you take a period of a day, and that certainly was stars they saw like that. Take 10 light years away, that may not have been known so well to them, and you calculate an H of 10 to the minus 23 for that system with a period of a half a day. It looks the same each time it goes halfway around. And that system, that 10 to the minus 23, is actually not so small. It turns out nowadays we can think of that as something measurable. But at Einstein's time, it was hopeless. And here's the way you could see that. If you just look at the system and see how much it changes due to the fact that it might be radiating, it has a Q of 10 to the 15, or a decay time of 10 to the 13 years. So it would take 10 to the 13 years really before you could see these two stars getting close enough so you could see, through a telescope, you could see a change. So you can see why he might have said this. So let's go to the next slide. Now, between this slide and that last one, there was a lot of work done by people like Joe Weber building devices that to try to directly measure these strains. As it's a long history, I don't think we go into that, and we don't have the time for it, but the thing is that the bars detectors that Weber invented with Wheeler together never made any measurement. They made measurements, but they turned out never to be confirmed by anybody. And their strain sensitivity was probably around 10 to the minus 15. That's what we now guess when you look at it. The systems that have made the detections, and this is an example of one, I want you to understand the device. That's what I made this picture for, is interferometric techniques. So these are techniques where you have free masses, not bars. And here the two free masses are told, you see in the picture, test mass 1 and test mass 2. They're the furthest mass in the picture. A gravitational wave is coming down on this system. And now this is a simple Michelson interferometer where the arm lengths, the distance in time for light to travel from the beam splitter, which is the center point, to the test mass 1 and back again is exactly the same as the time it goes from the beam splitter to test mass 2 and back again. Under those circumstances, no light gets to the photodetector. And I will not belabor this here for sake of time, but if you look at this picture, you'll see a very interesting feature which we'll need later, but maybe I have to belabor it a little bit. What I do is that there's a laser you can see on the bottom left. And you can see that there are these arrows. And the arrows, for example, that's leaving the laser, where you'll see a red arrow. And that red arrow is the carrier light in the laser. And the purple ones are the direction of flow of the light. So you can see as it leaves the laser light has only the carrier in it. It hits the beam splitter. Let's take a look at the one that goes left, goes to the test mass 1. And it gets reduced a little bit because it gets reflected at the beam splitter. And you can see it heading toward test mass 1. And then, because of the expansion and contraction of space due to the gravitational wave, which has a frequency which is very, very much smaller than the frequency of the light, you get sidebands on the light. And those are indicated in the vector that comes back from test mass 1. You'll see a blue one and a green one. And one will be at a frequency above the carrier frequency of the laser, and another will be below. And those two sidebands are a way of the modulation due to the change of space, or you can also think of it as the motion of the mirror that has been induced by the gravitational wave. So just follow now. Let's go back to the laser. Look at the other arm and see what happens. You go through the beam splitter. This time it's transmitted. Same thing, now you're going to test mass 2. Again, there's no modulation on the way out, which is a figment here. And later on, we may not need to use that. But anyway, come back from the test mass and you'll see the same modulation products, but they have the opposite sign. Remember, this is one of the symmetries of the gravitational wave. You get a stretching along one dimension that's perpendicular to the propagation direction and a contraction along the other. So the sidebands have the opposite signs. And that's very important. You come back to the beam splitter, and at the beam splitter, if you have arranged the times to be the same for the two arms, you will then cancel the carrier as you go to the photodetector that's on the right. But the two sidebands add up, and that's the key to the whole idea. So what happens is if you understand the diagram, you will understand the more complex version of the system that actually made the detection. What you're really doing is you're setting a system up where the gravitational wave induces sidebands on the light, and those sidebands are manipulated by different parts of the optics. So, and right now, in order to make those sidebands make current in the photodetector, you add a little bit of the carrier back to the system. That's when you beat the carrier against those sidebands. So let's go on to the next slide. It's all very easy to say, and that diagram is probably okay. But back in the early days of this, we didn't really know how strong the sources would be. And in fact, Kip Thorne and his group at Caltech was probably one of the most significant in the group, of all the people who had done studies on both what existed in the universe and also knew enough of the theory so they could say, look, if you ever want to succeed with a direct measurement of gravitational waves, you had to get the strains of the order of 10 to the minus 21. And that Weber was 10 to the 6 orders of magnitude away from that. So what that does is it threw a very interesting challenge to the experimenters. Because what it does, it says is, look, you have to get there two very nasty factors of 10 to the 12 that you have to solve as experimenters. Well, the first one is you have to, if you're going to use light, and time light, or use the wavelength, or however you do it, you're going to have to do the wavelength of light's about 10 to the minus 6 meters. And if you have a 4 kilometer long detector, which is what LIGO happens to be, a kilometer's length, you're dealing with motions of 10 to the minus 18 meters. So you're dealing with a thing which is 10 to the 12. You have to reduce, you have to make your ability to measure the motion of something 10 to the minus 12 times smaller than the wavelength of light. So that's your first challenge. How do you get light to do that? But that's not the only challenge you have. The other challenge is you have to make sure that the mirrors, or that objects that are doing the reflection of the light, do not wiggle more than 10 to the minus 18 meters, which means on the Earth, typically in the room you're sitting right now, the motion of the surface, motion of everything in there is at least a few times 10 to the minus 6 meters. So you have another factor of 10 to the 12 to go. And that makes life difficult. And that's why it took so long for many, many people to work on this thing to be ultimately able to make a detection. So let's go on to the next slide. Here then is the interferometer that actually made the detection. And I'll just show you some tricks that have been done to get that factor of 10 to the 12. And these tricks were invented by many people, Ron Drever among others, but a German group that had been at the Max Planck in Garching, and then the group in Glasgow, which was Ron's group, the group at Caltech, the group at MIT. A lot of people eventually worked on this thing and got this to the point where they got that factor of 10 to the 12 in the ability to read the position. That's not the only one. So what's been done here, you'll notice that in this picture, you see something you saw in the earlier picture. You'll see the beam splitter and the laser, and you'll see those distant mirrors, the ones that are far away. And now there's some new mirrors that have been put in there. The ones that are between the beam splitter and the test masses are partial reflecting mirrors that effectively take the light beam and let it bounce back and forth. And in LIGO, it's typically 300 times. Those are Fabry-Perot cavities. That's what their formal name is, but you can think of them as something that bounces the light back and forth 300 times. And that's true in both arms. You'll see that there's another mirror in the other arm too, the one with test mass 2. So, okay, now something I didn't tell you earlier was that if you now have no light going to all the carrier light none of it gets to the photodetector, it's all going to come back to the laser. That's where it goes. And that's something I didn't tell you when we were looking at the more simplified diagram. And that was both the German group, Schilling and Drever, had the idea of if this happens, what you do is this. You put another partially reflecting mirror between the laser and the beam splitter. Because now if no light's going to the photodetector, and none of the sidebands go this way, by the way. The sidebands are all going to the detector. So that none of the side, you don't ruin anything about the interferometer. You don't affect its performance as a detector of gravitational waves by putting that mirror there, or that partially reflecting mirror. You can do the following thing. You can take, and here's the way you see how it works. Imagine from the laser, you send a beam out, and it hits that what's called power recycling mirror, and part of it gets reflected because it's a partially reflecting mirror. There's also this beam, that's most of the light that went in the interferometer, except that got lost in the mirrors, that comes back through this mirror and through this power recycling mirror and is partially transmitted. Now you can take that reflected beam from that power recycling mirror and the transmitted beam and make them interferometrically cancel. And that's the idea. So what you do now is you have made it so if you can, and that's getting the coding on that mirror right and getting the position of the mirror right. If you do that, you have no light going back to the laser and all the light goes back into the interferometer. And you wind up with a situation where, for example, if you have 10 watts coming out of the laser, and you look at this cavity that consists of the power recycling mirror, the two input test masses, and the beam splitter, in that, you might have something like 500 watts. And then in the arms, you might have something like a half a megawatt. You have built up those sidebands that get generated by the gravitational wave. That's one of the ways you do to get this. And that was, in fact, that configuration is the configure that was run in LIGO and in Virgo, which is a detector that is in Italy. We'll get to it in a minute. Very similar to LIGO. Was run from 2000 to about 2010. One of the changes that was made for the advanced detector, which is ultimately what made the detection, is another mirror which is put between the beam splitter and the photodetector. You'll see it there. It's called the signal recycling mirror. And what that mirror does, it reflects the sidebands, that gravitational wave sidebands that were generated back into the interferometer for another go at being modulated by the gravitational wave. And that allows you to tune the response of the interferometer. It's a more subtle response, a more subtle mirror than the power recycling mirror. So let's go on. Here is the next slide, please. Here's now a picture. This happens to be for the initial detector. That was not the advanced detector, but you'll see, I just want to show you this so you can see what is the different things that make trouble, what makes noise. And the thing is, you'll see the shaded area, which is the area surrounded on one side by something called shot, and then near around 100 hertz, it's thermal noise, and then there's seismic noise. And the shot noise is just one part of the quantum noise. You're dealing with so many photons, and if you have photons, certain number of photons, you can measure the phase of the light only so well. So if you want to get the shot noise smaller, which is a quantum noise, you have to increase the power, and that brings the shot noise down. But at the same time, if you look over, there's a line that extends from there, from the shot noise to radiation pressure noise. You'll see that. That's going down, that's going up at low frequencies. And that is just exactly what it says, namely the radiation pressure of the light with fluctuations in it pushing the masses around. And those two things, the shot noise and the radiation pressure together, are the quantum limit for this particular interferometer and the macroscopic version with the mirrors of a Heisenberg microscope, that way you would normally think of an electron. It's exactly the same process. So that's the quantum limit. Then there is a other limit, which is the thermal noise. In this case, is the fact that these are suspended masses and they're hanging, and that's how you get the isolation, some of the isolation from the ground. But there is thermal noise, just a kind of Brownian motion, because you're operating at 300 degrees Kelvin. And in this case, the suspension's limited. And then there's the seismic noise, which is your inability, or in this particular instrument, the inability to get rid of all that ground noise, the noise in the ground. That all has been improved, as you'll see when we get to the advanced detector. On the other hand, the thing that you can't get, a very important noise, is a noise that you'll see all the way on the left. It's called gravity gradients, and it's the reason, and you can't do much about that. What that is actually very much comes from both density fluctuations in the atmosphere and density fluctuations in the ground. Both of these things make fluctuations in the equivalent mass that pulls on the mirror. In other words, a density fluctuation in the ground is a seismic noise, but it's not an acceleration of the system. It's an actual change in mass, and that mass, through Newton's, just plain old Newton's force, pulls on the mirrors. And the same thing happens in the atmosphere. And that's a system that, as you can see, is a dramatically increasing noise as a function as 1 over the frequency. And it's the reason why one has to go into space for detections probably below a few hertz. And that's not going to, you know, ideas of how to not get rid of it. There are ideas of how to measure attributes of the sound and make correlation measurements, but all of them look pretty, it's a very, very steep curve. So you might gain a little bit, get down to 1 hertz, but nobody has expectations to get down to fractions of a minute. And so the field for low frequency gravitational detection is not the ground. So let me take you on to the next slide. The next slide shows you the other factor, what was done for the other factor of 10 to the 12. This is now the ground noise. And this is now a big emphasis between the initial large detector that was built and the one that made the detection. And there were two things done, and I won't describe them very carefully, but just to show you, here, for example, this is a contribution made by the Glasgow group, is this thing on the right, which is 4 pendula in series. Each one has a filter of 1 over omega squared. So to get rid of high frequency ground noise, and you can see them, there's 4 masses all hanging. The bottom one is the one with the precious light on it, and that's the mirror. And then the suspension fibers were no longer steel as they were in the initial detector, but these are now fused silica fibers, which are far less loss, and therefore a lot less thermal noise distributed over a large frequency band. The thermal noise is now concentrated in a very, very narrow band, and thereby less disturbing. So that helps there too. And you'll see this when we get to the actual curves for the interferometer, how they work and what was the difference between the initial detector and the detector that did the detection. Then there was one further stuff, which is on the left, top left here. I won't describe that in detail, except to say that's an active vibration isolation system. And it consists of, you can see the 4 pendula hanging there. They're the thing that hangs down. But there are 2 stages of seismometers that measure ground motion. They're on the table. And then what you do is you measure that, and you have pushers that make the table go, the motion of the table go to 0. Sorry, let me say it carefully. You put a seismometer on the table. You look at the signal in the seismometer, which is a measure of the ground noise or the noise. And then you have forces that push on the mirror to null the signal in the seismometer. That's an active vibration system, isolation system. And that's how you get isolation at much lower frequencies. And that was absolutely critical for detecting the black holes. And the new noise curve, in principle, the noise curve for this detector, which is the one that's now running, or was running, and will run again when in December, it looks more like the curve that you see in the bottom picture. Now the big terms that are the noise turns out to be that red line that runs across. You can see it at the sweet spot around 100 hertz. That noise turns out to be the thermal noise in the coatings of the mirrors. And that turns out to be quite a problem, and it's a serious issue. And we, at this moment, the instrument that has been running is not even at that level. It's a factor of 2 at about 100 hertz, where we're not at what the theoretical limit is for this detector yet. And it's not yet limited by that red line. Okay, so let me take you on. Here then is the next curve is actually well, I guess I lied to you. I don't have a picture in here of the performance of the initial detector. That's a pity. But let me walk you quickly through this. You'll see this picture twice. Right now, I just want to point out to you that these are the noise curves. And I should have also said that this is appropriate to the other picture you just saw, that what's being plotted here is a spectrum. That's sort of, it's a strain per square root hertz. So if you want to convert that back into an RMS noise like that 10 to the minus 21 I was telling you about, you have to multiply by the square root of the bandwidth in wherever you're looking at what frequency you're doing the detection. So in this case, you can see the top curve, which is the Italian detector, the advanced Virgo detector. And that began running with us as very importantly, after, not right away, in the beginning of the LIGO run that made the initial detection. They were important. We'll get to that when we get to looking at the black holes and also looking at the neutron star collision. The initial LIGO detector, the advanced LIGO detector, is that purple line that's below, and that is about as good as we got. And you'll notice that there's something called the advanced LIGO design, which is in green below that. And that is the equivalent of the picture that I showed you in the previous slide. And you can see that the purple line is not at the advanced LIGO design curve. And that deviation, the difference, is a factor of 2, depends on what frequency you're looking at. And that right now is something we're working on very, very hard to try to figure out why that discrepancy is there. The advanced Virgo design, when it gets finished, will touch, and then you'll see it's specifically designed so that it meets the advanced LIGO design near 100 hertz. And then this is because there are a couple of things. They've made some decisions on Virgo. One of them is they're shorter than LIGO. LIGO is 4 kilometers. Virgo is 3 kilometers. But they made some decisions not to do certain optics. And so that eliminates their ability at high frequencies. They can change that. But right now, their whole attempt in their design is to get to so that at near 100 hertz, where a lot of the action has been, is that they can be equal partners in the detection business. So, here, next slide, please, is a distribution of where we are. This one we'll see twice also. The detectors that made the initial detection are the ones in the United States, the ones at LHO, which is up in Hanford, Washington. That's on the left. And then in Louisiana, there's another one. And these are separated by something like 3,000 kilometers. Then there's the Virgo detector. You can see it in Italy. And then there's a research detector, which is 600 meters long near Hanover in Germany. And I won't go into the others because they're coming. We'll talk about them in a minute. All right, next slide, please. And now this one, no, go back, please. Yeah, and hit that and make it move. Just hit it again and once more, and it should become a movie. Okay, I see. You have a PC probably and not a Mac. Yeah, the movie won't work. I am sorry. Okay, let's forget about it. What this was, a very short little picture of the LIGO sites. This happens to be the LIGO site. The one you're seeing is the LIGO site at Hanford. No, at Livingston, because that's trees. And then, but we're not going to be able to get the movie running. So let's go on to the next slide. That's right. Stay right there. Okay. I'm sorry. You can view this yourselves on the net. I put this on the net. So, okay, we're now getting on to what ultimately we did so we could have confirmation for ourselves that we detected something. This is an important slide in the philosophy of why we have multiple detectors and also why we built the detector we did, the way we did it. First thing is that what we demanded is that if we ever going to have a measure of a gravitational wave, it's very much like what Weber did. You had to have detections at both sites. And you had to have 2 sites. That was for 2 reasons. One, the 2 sites gave you the confidence that at least It was something that wasn't local, from the local environment, and it was something at least you think coming from something global. And on top of that, it gave you a little bit of information of where the source was, and we'll get to that in a minute. The other thing that's at the sites, and very important to us, is that there is a whole set of instruments that measure the environment. You can read them for yourself. I won't go into it, but things like measure the ground noise, measure the acoustic noise, measure the amount of magnetic field variation, the line voltage, all sorts of stuff. And that is actually a very critical piece of the detector, because if you see something that is coincident in the environmental system with something you think is in the detector output that you thought was a gravitational wave, you can use that as a veto. And there's an even more powerful part, which is the third part, which is the one at the bottom of the slide, which is a real luxury. I mean, it turns out that I never had been in an experiment where you could do what this is doing. What it allows you, and this is a very elaborate system of many, many locations in the detector where you have subsets, where you have subsystems, and you can measure the outputs of each of the subsystems. Like, for example, you can measure the laser frequency noise. You can measure the laser amplitude noise. You can measure the acceleration of the tilt motion of the suspensions. You can measure virtually everything you can think of. And there are about 10 to the 5 signals coming out, not necessarily with the bandwidth of the gravitational waves, but with sufficient information so that you can see if something's wrong in the instrument. And that also can be made to veto the signals. So let me take you now to the next slide. And that's everybody's seen this before. I just want to say something about it. This was the thing we detected, the black hole that we detected in September of 2015. And what I want to point out to you is that you can see the signal is on the left, on the top is the one at Hanford. Up to the middle of that, or from the left to about the middle of it is mostly noise. And then all the way on the right is mostly noise. But there's a significant coherent thing in the middle. And then on the next panel over on the right is the signal at Livingston, but shifted by 7 milliseconds. Because what happened is that the signal hit Livingston first and then came to Hanford. So we know from that alone that the source was in the south, but we don't know much more than that. Now, the next picture are numerical relativity solutions that are somehow the best fits to the data. In other words, in terms of the different parameters that are in the system, like the masses and the distance and the orientation of the orbit and so forth. And then there's a residual, which has been quite controversial. People have found systematics in that residual. And that turned out to be our own mistake. So anyway, the reason why I want to show you this picture is that this is what people saw directly. They saw it directly from a cross-correlation of the two detectors. In other words, you used the signal in one detector as the reference for a signal in the other detector, and you cross-correlate. And that's what you're seeing ultimately was used to get all the parameters. These are the individual signals in the individual detectors. And these things you could see directly by eye because they were filtered by this filter function that's on the top right. That's simply just a treble control and a bass control. So, it was very, very little done. It was just knock your eyes out how big this signal was. And at the bottom is a frequency spectrum. This is the time. You can see the very bottom picture is the time. It's about 0.2 seconds. And it runs from about 30 hertz. That's sort of the bottom of the noise curve where we would still detect something up to about, and this is not limited by noise, is about to middle C, 256. And that's when the thing crashes. At least that's what we think. And then these are the two sites. So here's what we think that is. That's the next slide. And this is just a gee whiz slide. The next one. Yeah, that's now a model. The model, by the way, doesn't look the same as the data. Why? Because it doesn't have that filter function that I just pointed out to you. It doesn't have that bass and treble filter in it. And that's what the model is. And what's going on, once we figured out, was that this is the two black holes. What they did was on top of this, and I'll describe them a little better in a minute. But they near the end of the signal of this thing, which is not noise. There's no noise in this because this is a model. You see the ring down of the metric, which happens after the black hole forms. We did not see that with any confidence at the very over on the very right. That's something that's in the future for us. But it's pretty gee whiz in some regard. Look at the green line at the bottom. Look at the relative velocity of these things. I mean, of these two things as they're orbiting. I mean, they're getting up to about 0.6 the velocity of light, and they weigh something like 25, 30 solar masses. So anyway, let me go on to the next slide. Okay, the next slide shows you a compendium of the things we'd seen up to this year. And there are 4 black holes systems. These are the 4. And the one we were just talking about is the blue one on top. It's the shortest one because it has also the largest masses. You can see also from the scales that you're talking about 10 to the minus 21 as sort of the RMS value of the peaks. And then there's the one we're not so sure of, which is the green one, and then we're quite sure of the red one, which is further on down, and the purple one. But let me dwell a little longer on something which is really quite amazing when you think about it, on the blue one, the one that we've been talking about most. The masses for those two guys is written on the right, 36 solar masses for one, 29 solar masses for the other. 3 solar masses are getting lost to gravitational waves. And this gives you, if you want to get some instinct about how difficult it is to squeeze space, just look at these numbers, the ones that I put below that. Suppose you took this whole system, which happens to be at about 1 billion light years away. All of these are of order 1 billion light years away. And put it at the position of the sun, just for the hell of it. You would experience an H here at the Earth of only 10 to the minus 6. I know you would barely measure that. You couldn't feel it. A change of 1/1,000,000th of your length or one of your girth, you're never going to feel that. You might hear a slight click in your ear because your ear is thermal noise limited. But what's going through you is unbelievable. It's 10 to the 25 watts per meter squared. I mean, the sun puts out 1,000 watts per meter squared in things that you feel. I mean, all the radiation that comes out of it. This is 10 to the 22 times bigger than anything that comes out of the sun. So it's really quite remarkable. And it gives you a feeling how difficult it is to squeeze space, or how much energy it takes to squeeze space a little bit. It's enormous. So let me go on and go on. The next slide. The next slide shows you the poor ability on the sky to be able to tell where those 3 sources are. Those banana-like curves have an area. That's just from the 2 detectors and knowing a little bit about the angular distribution of the detectors themselves, which isn't completely spherical, but it's more like a peanut look. That's what it looks like, a peanut. And the area of the sky of uncertainty is about 1,000 square degrees. So that's really not a very nice thing to give to an astronomer, to try to have them try to find this thing. This has been a problem. Now the next slide is a completely new situation. This now is a triple coincidence, and this is the importance of Virgo coming on the air. Because now, and you can see it from the date, this is October of last year, we saw, this is now the 5th black hole coincidence, collision, and you can see that the signal noise isn't as good as it is. The Virgo detector is the 3rd one over from the left. Well, yeah, it's the 3rd one over. But it provided enough so you could reduce the error circle. And that's what I want to show you. That's why this slide is here. The error circle with the LIGO detectors alone, if you look at the sky down below, you'll see that there's this banana-looking thing, and that is about 1,000 square degrees. And now you add to that the measurement made by Virgo, and you can see well, depending on what assumptions you make, it's either the green one or the purple one. You've got that down to about 100, somewhere between 30 to 100 square degrees. It's a hell of a lot better, but still not wonderful for an astronomer, but it's a hell of a lot better. So you can see the importance of this network, and we'll talk more about that as we go on. Next slide, please. Yeah, this is sort of just an advertising slide of all the different pairs that have been measured. And it shows you that all the ones we've been seeing are pretty big. And the ones that people had seen before in binary systems, stellar systems, are the ones on the left and lower down. And those are the black holes. So these are large. We don't know exactly where they come from. That's one of the challenges. It's interesting, and I know a lot of people are thinking about whether they are primeval, or whether they are something that came from common envelope evolution, or come from collisions in clusters. I mean, we don't know yet. And that's something that we'll get more as we get more of these and get deeper into space. We'll know a lot more about this. So let me go on. The next slide, please. Okay, the other big event, and this one is really quite a different kind of structure entirely, is the one that just took place again last year, but at the end of this year. And this was, you can see the signal. It's on the bottom panel in this thing. The signal in this case, this is again one of these sonic diagrams, and it lasts in the band of LIGO for at least 10 seconds. You can see it, and it's a chirp. I mean, the kind of thing that we've always talked about, namely that you can whistle, you know. And then there is this remarkable thing that was seen, which is in the upper panels, and I know at your conference you're going to be talking about this a lot. Is the Fermi gamma ray telescope the measurement of a gamma ray burst that is about something like it looks like 0.7 seconds. Yeah, no, it's more like 2 seconds later than the moment from at which we don't in the gravity wave thing, we don't see the collision directly. They're getting very, very close, but that happens more at a kilohertz, and our sensitivity isn't good enough at a kilohertz, so we can just about see it at 300 hertz. So it's a little bit later, but not much than you see in the picture at the bottom here. So anyway, there is a gamma ray burst of a short variety seen by Fermi. It's seen in both instruments of Fermi, both the low frequency and the high energy and the low energy instrument, and seen sort of in another satellite also. And that was a very important business, that it was seen by electromagnetic astronomy. And I just want to show you why it wasn't immediately announced, and that's the next slide. This is sort of this is a rare event in our system, but it happened at the wrong moment. You'll see up on the top left there, you see that chirp, but now this is a chirp in Livingston. And what you'll see there's a big ugly thing that we think it's a dropout of a servo because of a piece of dust falling through the beam. But anyway, it's much, much larger than the signal, as you can see in the frequency. And what happens is that you can see the chirp behind it, and it's not hard to remove it. And there's a technique for taking that out. And that's in fact how the best signal noise was achieved. But I'll tell you what it did. The fact that we had that was made a veto for the entire system. See, it's part of that thing I showed you in the slide where what we demand as being something detectable. We demand the signal be the same in both detectors, but it wasn't. There was this big spike in the one in Louisiana, and so what happened is our automated system canceled this as an event, and people saw this thing, and they had to do this by hand. They saw the thing in Hanford, and then they looked at this thing in Louisiana a little bit later, and they saw this thing, and then it took a little while to get rid of that spike, and that's ultimately what gave the position for the position that comes from LIGO. But so let me go on the next slide, and there is now another piece to this, which is that Virgo did not see it. Now that sounds very strange, but Virgo should have seen it. In other words, it was strong enough in LIGO. We know it, having seen the black hole in Virgo, we know it's working. And on top of that, we know the sensitivity of Virgo. Virgo should have seen this neutron star binary also, but it didn't. And so consequently, we got information out of that, which actually narrowed the error circle on the sky a lot. Because what it said must have been in that spot of the peanut, where there is less response by the detector. And indeed it was. And this is what this shows. So you see in this picture here, all the different sky locations that were afforded by these different instruments. For example, you'll see the green extended one is LIGO alone. And then in that is the LIGO Virgo together. And that's the best identification for the position. There's the Fermi identification. It's kind of broad. You can see it's that circle that runs around it. And then the integral thing in Fermi, the low frequency, the low energy instrument, is this huge banana. So in other words, this position was determined fundamentally by, and reason why this really succeeded so well was because of Virgo together with LIGO. And within about 6 hours, people saw this thing. And I don't know, all the astronomers got mixed up in this thing, and very many of them. But the pictures on the right indicate that the Swope telescope, about 6 hours after the event, and saw they had been pictures of the NGC 4493 galaxy something like 20 days before, and they don't see a dot where the little arrow, the little pointers are. And now, right after this event, there it is. There is a dot there, and that, in fact, drew a huge number of people in the astronomy community to go to that place, and they were very successful. And in fact, they found, and in the next slide, this is just a slide, the next slide, please. Yeah, the next slide sort of indicates, if you look at it carefully, and I'm not going to do it with you, it shows the different times when the time is going on as a horizontal axis, and different techniques, gravity waves, gamma ray, X-rays, UV, optical, IR, radio, and where's the X-ray? Yeah, there it is. When they made observations on this thing, and little by little, they figured out exactly what was going on. And that, by the way, was the big event for everybody that came in this last few months. So, what is thought? And you're going to have a lot better explanations of this than I can give you at your meeting. But it is thought to look like this picture that you see in the next slide. And it is thought to be, and I know there are many papers out on this, and I'm probably way behind on that. But the thing is that here are the two neutron stars coming in, those blue, coming in together, and they form a new black hole, which was probably only seen after the X-rays and the radio got seen, and then the gamma ray is a little off axis, and that's why it's a weak short gamma ray. And what this whole scene, with the fact that you have measurements of the formation of the black hole, probably, but more importantly, you see that whole gas of neutrons and the high energy neutrons coming together, and with other elements, with other nuclei to make the heavy elements, is something that was actually predicted by Svi many years ago, in 1989, along with speed. This should be a real triumph. And it's, so anyway, so let me go on with the next slide, because you're going to do it again. And what this slide shows is some of the modeling that has been done on and measurements that have been done from different techniques on showing that you have broad bands of lines. You don't see the individual lines, which I find as a big disappointment. In fact, I didn't realize that until fairly late in the game, that the velocities of the ejecta are so large in this thing that they're so broad that they're Doppler shifted and broadened because there's so much turmoil going on in that cloud that you don't see iron, you don't see gold and platinum and uranium lines. You see things that have been modeled at Oak Ridge and also at Los Alamos when you have collisions of collisions of neutron stars. And you expect then that there will be a very sharp drop in the blue lines and when the lanthanides get made after a very, very short time. And that as this thing cools off, and you can see this in this picture, the longer wavelengths persist longer. And that the detailed model of this has been done by a lot of people. Metzger is one of them, but that's the one I know. There are probably others. And they seem to fit the idea that this is indeed the R process at work. Now, there's lots of stuff at your conference about this, and maybe everything I've said is wrong. Okay, let's go on. The thing that was sort of a cute sideshow in this thing is the fact that you could get the Hubble constant, not as well as you can out of Planck or the supernova yet, but ultimately it was sort of interesting to get it by a completely different method. The idea here, and you can see this, in this picture, you can see the orangey brown thing is the supernova. The value for the Hubble constant is on the x-axis, and then the Planck, that's the 3-degree one. Using the 3-degree the acoustic peaks in the 3 degrees, you get the bluish one, and then this curve, which is not anywhere near as defining as these other two, almost. That comes from modeling the following. It's fairly straightforward. You have now, you know the Z of the galaxy because it was identified. That's important. And now you have another way of getting the distance, which is you get the distance from the following. You have the gravitational wave signal. You have identified it as, you get the masses out of that from the frequency, and you get the distance from the amplitude because you believe the Einstein field equations. So consequently, you're using Einstein's field equations, the fact that you identified the masses from the dynamics, and that allows you to get an amplitude reduction between where of h at the source to at the Earth. And once you have that you know the distance, and that's the fit you get. This curve is the fit you get to the Hubble constant. It's broad, and if you do this with many more systems, it's going to be very interesting, and it has completely different systematics than either of the other methods. So it has its own value. And that's something Bernie Schutz pointed out many years ago. So let me go on. Okay, so I quickly want to say before there are other sources being looked at. I'll quickly show you that. And I don't want to take the time because I'm running out of time. But let me show you some results from other sources, and that's the next slide. And this may take a little while to come on. Oh, it came right away. Okay, so what it is, for example, there's within LIGO, there are people always looking for CW sources. And here's a map that they've made of CW sources as a function of frequency. And they've mapped out dots in here. The dots, which are little stars, are the ring down values you would expect sorry, let me say it carefully. It's the H value you would get from a pulsar at that point which you have identified if all the energy that was being lost by the pulsar and you get from the period change was coming from a loss due to gravitational waves. Now that's not the case, but we are now finally getting to the point where the ring down values for H are getting to the point where you can look below the electromagnetic one. And so that's going on. That'll continue to go on for a long time. The picture on the right is something quite different, and it's something which many people don't know about. It's a radiometer search for gravitational waves. That's also going on. And what that is that what you do is it's the way you do the analysis. You look at something like Sirius, you look at an X-ray source, or whatever you think you want to see, is it also radiating gravitational waves? What you do is you continue to co-add that point in the sky with another relative to another point. And you keep co-adding it every time the detector and the Earth has put you in the right position so that it's maximized in the gravitational wave detectors. So it's effectively co-adding the gravitational wave strength from a given region in the sky. And people are doing this, and maybe we'll find sources they don't understand this way. This is a nice way of looking at the sky. Finally, here's a thing that's going to happen, which is the next slide. And that is, if you are looking at an unresolved set of black holes, and we now know a lot more about how many black holes there are, you will get what's called in the CMB business a foreground, but in our business is called a background of just unresolved black hole signals. And we continually do that by cross-correlating the detectors. And that's done as a matter of one of the sources that we look for. And you can see here, for example, the noise level that is expected in the system in the future, this the next couple of runs, sort of gets into the region where you get down to something which is predictable, and people think they might see a gravitational wave noise that comes from black holes that we already know about at a level of about 10 to the minus 9 of closure density. So that's the thing that's going on also. Okay, now the last piece of this is about the future. And can you tell me if I have enough time to do this? It's about 5 minutes more. Hello? Can somebody tell me if I have enough time? Okay, I'll take the time.
Well, I think you should carry on anyway. So
okay.
I'll reduce the amount of questions.
Okay, good.
Okay.
So anyway, this picture, which is the next slide, is the one you have. Shows some things which I didn't talk about the last time. You'll see Kagra, which is in Japan, and that's a new detector probably by 2020 or something like that, we hope. And then there's one called LIGO India, which is something which is LIGO, one of the detectors of LIGO being placed in India. So there were 3 initial detectors. there were two in one envelope on LIGO, and one of the ones that was in the envelope at Hanford was brought to India. And the idea of this is to increase the precision of being able to see the thing on the sky. So let me take you to the next slide. And the next slide shows you what happens if you have Hanford, Livingston, and Virgo. That's these pictures of the sky with their bananas. And these are for different signal noises, starting from the top left, going right and down. And if you now add India to this, you'll see that the thing cleans up quite nicely. And you will then have, it's enough out of the plane, and so you can begin to get, it's a little bit of an exaggeration, you begin to get sizes of the order of a couple of moon sizes. And that becomes very important for astronomy, to be able to couple the gravitational wave sky to the electromagnetic one. So let me go on to the next slide, please. And this is that slide again I showed you before. And I want to now emphasize what's on the bottom of that slide. In other words, we hope with LIGO now to get to the green line, which is the advanced LIGO design within the next runs, the next two runs. There are already plans afoot with new ideas, in particular trying to fix the coatings, squeeze light into the system, well, that's already being done, to get to the blue line A+, if you see that. So that's another factor of about 2.5. And then there are ideas for doing things that get around a lot of the thermal noise in the coatings, and maybe using some cryogenics, which are called Voyager. And that's this purple line called down, another factor of about 2. And then there are ideas both in Europe and in the United States for doing something really much more bold. And that's, in Europe, it's Einstein B. You'll see that's lower. That's building a triangle, a 10-kilometer triangle underground. And then there is, in the United States, the idea of looking at above ground, 40 kilometer Ls. And those are called Cosmic Explorer. I'll show you, now let's go to the next slide. I'll show you one modeling result that has come from this. And that is this picture here is sort of quite dramatic. This is a picture. Should you get to either the Virgo or that Einstein telescope or the Cosmic Explorer, you would get this kind of, it depends on, this is now a picture of the signal to noise you have versus redshift for 30 solar mass black holes of order. And you'll see that you can see the whole universe. And you can see the whole universe in the black holes that we have detected. That would be quite spectacular. I mean, you could tell where they come from. You could use them for cosmology. That would be a dramatic change. But you have to change the instruments. We'll work toward that, but this is what the future may hold. And now the last slide is sort of what the whole field is, and that's my very end slide. This is a picture which is mostly to show you what's going on. I won't be in great detail. This is a picture where frequency of gravitational waves is the x-axis, and RMS strain H is the sort of an indicator for the y-axis. And you can see LIGO and the type of sources it's doing on the right, with with periods of frequencies of a few hertz to 10 to the 4 hertz. But then there's LISA, which I wish we had more time to talk about, which is doing this. LISA is almost as old as LIGO. It's doing a triangle in space, and it will cover a wonderful range of frequencies. The range of frequencies from about periods of an hour to maybe fractions of a minute. And it has in it massive black hole coalescences. And also probably the most significant tests we could make for small masses falling into black holes. These are the tests for general relativity. And it also sees white dwarf binaries. I mean, in fact, there was a worry that they would get swamped by the gravitational wave signals from white dwarf binaries. But that's not a problem, at least now that people have modeled it better. Then at even lower frequencies, there is the pulsar timing system, which is already going, and it hopes to see gravitational waves coming through our galaxy, doing the following: taking millisecond pulsars, hopefully a good distribution of them over the sky, and finding that, let's say, the ones in the north and the ones in the south slow down a little bit in their rate, and the ones in the east and the west speed up in their rate, as a gravitational wave of periods of years to, threes of years, maybe to halves of years, comes through our solar system, comes through our galaxy. And finally, I won't describe this very much, but this is an ongoing system which is all the way on the left, probably to me one of the most exciting experiments you can do. is the measurement of looking for primeval gravitational waves that might have come from inflation. And people are doing that by looking at the polarization of the gravitational wave, cosmic background. And that's an ongoing experiment. It needs many channels so you can get rid of the problems that Weiss had, namely that you want to be able to separate, in this case, foregrounds like dust and free emission and synchrotron emission from the cosmic background, which, and look at these polarization patterns, which are characteristic of excitation of the plasma in the primeval plasma, which is the sort of 300,000 years after the explosion. The plasma getting density changes due to the gravitational waves. That's what causes the polarization. So thank you very much, and I'm sorry I was not there.
Thank you. You hear the claps?
Yeah, I agree.
Right, so since we are grossly over time, can we, is there any question? Yes, Masha. So Masha Duclois.
Yeah, you spoke mainly about optical detection of a gravitational wave. Instead of using optical interferometry, I mean, there are proposals now to use atom interferometry. And in this way, we could have access to different frequency range and stuff like that. What are your comments about that?
Yeah, you ask a very tricky, hard question. The question you're asking is really, where does atom interferometry fit into this scheme? And I looked at that very hard when the people at Stanford were pushing atom interferometry as a way of replacing LISA, which I found not sensible. There is a very good place for atom interferometry, which I think is being done in France at this moment, the MICA project, is to actually look at the gravitational gradients. That thing I showed you in the noise curve for the initial large detector, you saw that curve that comes up at an incredible rate as 1 over the frequency to some power. That could be measured, though that noise could be measured. Unfortunately, it also can't separate it from gravitational waves. You get both the gravitational waves in the periods of around a second, maybe a fraction of a second. And you can then measure that geophysical and that what we call the gravitational gradient noise. That's an extremely important measurement to make. And the reason why it's good and why it's not so easy to make on the ground without atom interferometers, it's hard to make the suspensions. See, the atom interferometers throw the atoms up in clouds. And so you don't have to make a suspension, and you can solve for the velocity of the cloud as it was launched. So you can do a lower frequency measurement. The real problem with and there's been many comparisons made of optical interferometers vis-a-vis atom interferometers. There's a paper written, I'm trying to think of the person who's at Berkeley who was part of that. It'll occur to me. But anyway, they compared atom and optical interferometers on the ground and also in space, and found that there was no strong advantage. And in fact, it looked like what's the limit is the number of atoms you can put into the cloud before Stark effects and other collisional problems become an issue. Look, you may have other arguments for it. It's certainly a technique, but it's not the grand world-beating technique that was claimed by the people at Stanford when they first made the noise about beating out LISA.
Right, thank you. We'll allow one more question, the last question, yeah.
So are there any technical limits on the lifetime of LIGO?
Yeah, there are plenty of them. You mean technical in terms of things corroding and the tubes disappearing? No, or do you mean, are there things that stand in the way of doing better? I think that right now, the curves I showed you, the curve that was what's called Voyager. I'm sorry, we could bring it back. Maybe we could do that. If you click back, you'll find the Voyager curve if you want to do that. Voyager is sort of right now the best we can imagine we can do in the 4-kilometer systems. On the other hand, we think by going to the larger systems, and we can do better, as you see in the bottom of that curve for Cosmic Explorer. It's just a big deal. We got a lot of money, and we have to think of how to make that cheap enough so that we can all afford it.